So before we get started taking notes in section 10.3, please make sure that you have printed out the PowerPoint, and we'll see what we can do working with all 6 trig functions. As we work through our 6 trig functions, we're going to use sine, cosine, and tangent regularly, and we have a helpful acronym, SOHCAHTOA. And this helps us remember the relationship of the sides of the right triangle. Here's my right triangle. In reference to our angle. From our angle, we have the side opposite, we have our side adjacent, and we have the hypotenuse of the right angle. And this helps us establish the ratio of the sides to give us the sine, cosine, and tangent. The sine of the angle is the ratio opposite over hypotenuse. Cosine of the angle is adjacent over hypotenuse, and tangent of the angle is opposite over adjacent. And we can recall this using SOHCAHTOA. Now we can continue, or we can expand upon this idea if we have our angle. We call it standard position. That just means it's starting on the x-axis and going up to some point. All of your paper, I think, uses theta as some angle. R is going to be our radius. And to find the value of r, we're using the equation of a circle. We use x squared plus y squared equals r squared, and then to get r all by itself, we take the square root of both sides. And then this allows us to establish our right triangle here. The x value and the y value of our triangle. Our angle is here, and again that would be theta, which here is denoted by a box, and I think on yours has a nice theta symbol. And so we can create relationships between the hypotenuse, the side opposite, and the side adjacent using the now 3 labels that we have on our triangle with there's our angle, there's r, there's x, and there's y, and we can have the 3 that we looked at just before, sine, cosine, and tangent, and then we can come to cosecant, secant, and cotangent. These are the reciprocal trig functions. So all of the fractions have been flipped. Sine was y over r, cosecant is the reciprocal. And I don't have a good memory trick for secant and cosine, or cosecant and sine, other than to say that the s's and c's go together, which is not that helpful, but maybe you have a better one. So we want to take an ordered pair, 12, 5, and figure out all 6 trig functions, the ratio of the sides. So most of them contain an r value, which means I need to find r using the Pythagorean theorem, since I have a really nice right triangle here. X squared plus y squared. I'm going to take 12 squared plus 5 squared, which is 144 plus 25, which I think gives us 169. And amazingly, that's a perfect square itself, so r equals 13. And we're going to work with the 12, the 5, and the 13, and all 6 trig functions on the next slide. So here we go. R equals 13, y is 5, x is 12. So sine of my angle is 5 over 13. Cosine is 12 over 13. Tangent is 5 over 12. And now for the last 3, I'm just going to flip my fractions. And we have all 6 trig functions based off of the right triangle that we had from that ordered pair. Now I have no idea what angle, oh, I guess it was theta. Okay, given that theta is an acute angle, the cosine is 8 over 17. All right, so cosine, here's my somewhat drawn to scale triangle. Here's theta. Cosine tells me adjacent over hypotenuse. So I need to go find the missing side. And let's see, that's 289. Equals 64 plus y squared. If I subtract, I wind up getting that y squared equals 225, and that tells me y equals 15. So I'm going to make my list with sine, cosine, tangent, and then I'm going to line up the reciprocal trig functions, cosecant, secant, and cotangent. Okay, so sine would be 15 over 17. Cosine, they told us already. Tangent, and then for my reciprocal trig functions, I need to flip my fractions. And there we have it. So for this question, it's giving me some information about cosecant, which is 1 over sine theta is 1.02. And so I need to figure out the information of theta that we have here, and then I can use that to find the tangent. So if I want to find the sine of this angle, I need to use the reciprocal of the 1.02, which is not how a mathematician likes to write these things, but this would be the easiest way to understand what we have. So if I want to get an angle by itself, I need to use the inverse. And when I did that on my calculator, in degree mode, I got 78.3 635 something something something, big long decimal, degrees. So now that I know the angle here, it's, about 78, 79 degrees, I want to find the tangent of that answer, and it's not a pretty result, but the tangent of, say, 78.6 something 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 is 4.9, it says 3 significant digits, 8. And so that's my final answer. We talked about the 45, 45, 90 and the 30, 60, 90 triangle in class the other day. But when we did that, the circle that we were working with was a unit circle. So the radius, or the hypotenuse, was 1 in each case. And my diagram here is slightly different. I made our calculations a little bit different so that the length of the legs that were the same is now 1, and then we could find the hypotenuse using the Pythagorean theorem, which might be a pain when we're going through some of these trig functions. So let's see what happens. I know that sine is opposite over hypotenuse, and we've seen 1 over the square root of 2 before, and when we got rid of the square root of 2 in the denominator, we wound up getting the square root of 2 over 2. And same thing happened with cosine. And tangent, it's actually, we could do square root of 2 divided by square root of 2 over 2, or we could look at the fact that it's opposite over adjacent, which would be 1 over 1, also known as 1. With our reciprocal functions, I'm going to go back to the original 1 over the square root of 2 and flip that, and then secant's going to do the same thing, and then cotangent gives us a 1 again. In our 30, 60, 90, instead of using 1/2 as my side length and 1 as my radius for the unit circle, I made them whole numbers, and now I'm going from 30 to go opposite over hypotenuse, and adjacent over, whoops, that's a 3. Let's try getting the right numbers in there. Square root of 3 over 2, and tangent was opposite over adjacent. Get rid of the square roots. Okay, and then we need to flip our fractions for the reciprocals. Unfortunately, puts a square root in the denominator for secant, so I have to get rid of my square root. And cotangent, I'm going back to my original and flipping that, and there we have it. And you can work on this one all by yourself. Okay, so it's completely impossible to read what's on the screen here, where we're trying to find something to 3 significant digits, but hopefully on yours it's easier to read. We're trying to find the cosecant of 84.1 degrees. So first thing first is we want to make sure our calculator is in degree mode, because 84.1 degrees is not one of the degrees on our unit circle, so we have to use a calculator. Then up here we could use the reciprocal that's on our calculator, but we don't want to use the inverse, like to find sine inverse of an angle. this about the reciprocal is saying we could use sine of, in this case, 84.1 with the little -1 there, but not this that requires the second key. I don't like this notation because I think it helps you get confused with this one. So I'm going to show you a different procedure. We know that cosecant of an angle is 1 over the sine of the angle. So if we have the cosecant of 84.1, that is 1 over the sine of 84.1. So on my calculator, I put 1 divided by the sine of 84.1, and I get 1.0, and then it's another 0, but it says 3 significant digits, so I'm going to round 1, and that's my answer. In my second question, it asks about cotangent, and we have degrees, minutes, seconds. 14 minutes, 38 seconds. So again, I'm going to take cotangent, and that is 1 over tangent of this gorgeous angle. And on my calculator, putting in 57 degrees is not difficult. So 1 divided by the tangent of 57. And I can put in degrees, minutes, seconds in here, so somehow I'm going to go find that. And I can put in degrees and minutes under the angle. Alright, so first I'll put in degrees, and then 14 minutes. Do not put in R. And then I'll put in 38 divided by 60 just because I don't want to go looking for seconds. Syntax. Alright, never mind. Let me figure out what to do. Okay, so I found the seconds information. To put in degrees and minutes, you have to go to angle, which is second apps on the graphing calculator, the TI 83 or 84. So we can do that for 57, we put the degree, then 14, we put the minutes, and then to put the seconds, if you look on your calculator, above the plus sign, it's in alpha, like it's the green, there's the 2 lines for the minutes, so you have to press the alpha key to get that notation in there. So let's see what happens when we do 1 divided by the tangent. And beautiful decimal. There we go. So this chart helps give us some idea as to how many decimal places we need to have when we have a degree or a decimal to the nearest second or to the nearest minute to help us tell us how many decimals we need to have in our answer. Now we've used inverse trig functions like the inverse sine a little bit in class, but if we're looking at the notation with that little -1, when we're talking about, say, sine, cosine, or tangent, we are trying to find specifically the angle that makes this happen. So usually we would see something like the sine inverse of a fraction, like that's the ratio of the 2 sides of our right triangle, and we want to know what angle is in the triangle where these two sides take place. So if we have the question, like we're trying to find the arc sine of 1/2, we want to know what angle is it where the sine, so the sine of what angle is 1/2. That's like what we're mentally asking ourselves. And again, this is the only one that I have memorized, that the sine of 30 is 1/2. And so my angle theta would be 30 degrees. So in these couple questions here, we want to find the angle that gives us this relationship for tangent, where we have, opposite and adjacent. What angle does that happen at? So I need the tangent inverse of 3/5, and I'm going to check my calculators in degrees. It is. So the inverse tangent, or the arc tangent, of 3/5 is a little over 30 degrees. So 30, and it's 0.96, and this said to the nearest tenth, so that's going to make this go up to 31 degrees. Okay, and then this one was the sine of theta is 0.25. So I'm checking the arc sine of 0.25 equals 14.48 degrees. And you can practice a couple more of these to make sure you can find the inverse to get the angle. In the next couple examples, we are looking to find all of the missing pieces in our triangle. We have a little bit of information here. They're telling us angle A is 63.2 degrees and little a is 11.9 inches. And we know we have a right angle at angle C, so we need to find the missing pieces. Well, finding our angle B is going to be the easiest. 180 minus 90 minus 63.2 equals angle B. So 90 minus 63.2, angle B is 26.8. Okay, but now I need to find at least one of the other sides. And let's see, from my 63, I have opposite, and maybe I'll go find hypotenuse. So opposite and hypotenuse is the sine. Opposite is 11.9 over C. And I have this nice ratio here where I can cross multiply. And then to get C by itself, let's find out. So that's about 13.3 inches. Now, I'm not going to use my approximate value for C. I need to work with the information I was given to go find B. I now have opposite and adjacent. So opposite and adjacent sounds like tangent. So again, I will cross multiply. and solve for b. And I find out that b, if I round to 1 decimal, is about 6 inches. So in this problem, I find out that little a, that's a side, is 7, and little c is 9.3. So I have two sides of a right triangle, and I can go find the missing side. And if I take the square root, get a beautiful answer for b. I'm going to round that to 1 decimal place, just like a and c. And I don't have a unit this time, so that's just my value for little b. And let's see, if I look at angle B gives me an adjacent and a hypotenuse. So adjacent and hypotenuse, here I'll make it in black this time, would be cosine, and I'd have 7 over 9.3. So to get b by itself, I would have to do an arc cosine or an inverse of that fraction. And let's see, I'd get about 41.2 degrees. So I now have two angles. I have the right angle and I have angle B. I could easily go figure out angle A. And there we go. We've solved all the pieces that were missing. We found all of the sides and all of the angles in this triangle. Now, because we're using right triangles, there's a lot of word problems that go along with this, and we want to make sure that we know where these words are telling us, or what they're describing for us. And so the angle of elevation is at the ground, because we're looking up, like here's where we're looking, that's our eyeball, and it's from the ground. So pretend you're lying on the ground and your head is looking up. The angle of depression is outside here, looking down on the object. But what's really interesting, if you recall from your geometry, this horizontal line and this horizontal line cut by a transversal. Okay, that was a lovely transversal. If we have alternate interior angles, they happen to be the same. So angle of depression and angle of elevation can be located in the same spot, if you see what I mean. They won't be the same value necessarily, but you can put them in the same location in your diagram.